Welcome to Thursday lecture. We are going to continue with routing, and if you recall, we finished link state routing, so today will be distance vector routing. If we can finish this today, then we can say that we have done the network layer, and then we can move on to the data link layer next week. Next week lectures are already out in WebCMS in case you want to have a look. So let's go straight into distance vector routing. However, before we go to distance vector routing, let me just recap the link state routing. In the link state routing, it was flooding based. So every router would flood its link states to its neighbors, the link cost to its neighbors, to all the other routers. As a result, every router will have the complete global network connectivity graph. And once you have the graph, you can use the graph theory, Dijkstra's algorithm, to find out the shortest path tree. And from the shortest path tree, you can find out the next hop information to create your forwarding table. So that was the process. However, in distance vector routing, we are trying to avoid this kind of flooding and creating the global knowledge and creating the shortest path routing computations. Instead, as we are going to see, distance vector is completely different. It doesn't require centralized information. It's a decentralized system. So let's have a look how distance vector works. Okay, it's also known as Bellman-4. In recognition of the scientists, Bellman and Ford. So what you see here is the same graph that we used for link state routing, so it's easier for you to compare how we do the link state routing and distance vector routing. So instead of going through lots of mathematical notations and formal equations, let me just explain you very quickly, intuitively, what Bellman-4 is. This is very, very intuitive. So if this node U is interested in finding out the distance to its destinations, the first thing it has to do is look at its neighbors, right? That's all you can do. That's the first thing, because you know you can reach to these neighbors with certain cost. You know the link cost. So you start with your neighbors and see if this neighbor has an estimate to a particular destination. So all you have to do is get to this neighbor and then add the neighbor's estimate. So to get to this neighbor, you know the cost. So you add that cost to the estimate that this neighbor is telling you to reach to another destination. And that's your current estimate. And this can only improve if everyone will exchange their information with each other, with the neighbors that we will see later. So in this case, for U, it can go to X, it can go to V, and it can go to W, right? It's 3. So it can go to X with cost 1, it can go to V with cost 2, and it can go to W with cost 3, with cost 5, right? And let's say that V is telling you that, exchanging this information, V is telling you that I can reach another destination called Z with a cost of 5. The reason V says 5 is perhaps V has found out a route like this, 2 plus 1 plus 2. And W is telling you that, hey, I can go to Z with cost of 3 because probably it has found this path, right? 1 plus 2. And similarly, X says to you that I can reach to Z with cost of 3. So what should you do? So you just takes the minimum. So if it accepts V as its next hop to go to Z, then the cost would be 2 plus 5, right? So 2 plus 5, 7. If it chooses to go via X, then go to X is 1 and x is saying I can go with cost of 3 to z. So it would be 1 plus 3, 4. And if it listens to w, then w, to go to w is already 5, and w is saying I can go 3. So it's 5 plus 3, 8. So if you look at the minimum here, the minimum is 1 plus 3 is equal to 4, and it's coming from x. So you would say that, oh, I can, the minimum shortest path for me for now would be next hop x, and my cost would be 4 if I want to go to z, right? So this is the Bellman-Ford logic. You always look at your neighbors and see what the neighbors are telling you, right? So the idea is that you will regularly exchange information with your neighbors only. So this is very important. So if you look for differences between link state routing and distance vector routing, this is one of the differences. Link state routing, every router exchanges its information with all routers in the network using flooding. In distance vector routing, a router exchanges its current estimates routing table with only its neighbors. So if you have 2 neighbors, you exchange with only 2 neighbors. You do not flood. If you have 3 neighbors, you exchange with 3 neighbors. Do not flood the network. This is a significant difference between link state routing and distance vector routing. So in the Bellman-Ford, you can see if you just use information with your neighbors to find out the shortest path to destination at that stage, right? We'll see that it needs to iterate multiple times before it converges to the shortest path routing tables. Any questions so far? How we are getting that 4, minimum 4, to go to Z for you? Anything you would like to ask me? I will move on and show you more complicated networks. So if you have any questions, this is very fundamental. This is a very intuitive reasoning behind the Bellman-Ford or distance vector routing. Yes? I'll give you a microphone because this room is big and it doesn't get recorded. So it's for your own benefit. So when you listen to the lectures, you can also listen to the question, not just my answer.
So it keeps asking for the answers if it doesn't find the answer from the neighbors?
Yeah, so it's a very good question. So how does it get the information from the neighbors? Yeah, so we will visit this issue later, but I can tell you now that in real systems it's periodic. So every 30 seconds or something, you have to exchange the information. Any other questions? This computation, is that clear? The minimum? Okay. As we look at more concrete examples, this should get better, but we can always go back, right? So that was the question. So from time to time, so every 30 seconds or something, it will update its distance vector to its neighbors. And when you get the information from your neighbors, you have to recompute, right? Because the neighbors may be telling you some new information that you didn't know. The cost might have updated, right? The neighbor may have learned a better cost, a better route to another destination. So when you receive from the neighbor, you have to recompute what you have done before, right? And as a result of recomputation, your estimates to destinations may change. And if it change, then the next time when you exchange your information with your neighbors, they will also know the change. So all this change will propagate through the network as you are iteratively exchanging with your neighbors. So that's the whole idea. So you can see that either you can wait for a change and then you recompute, and if it changes your routing table, then you exchange. You can do that if then else, but instead, in practical systems, every 30 seconds you do it anyway, right? Because you don't want to wait. If then else means the system can hang, right? If something goes wrong and you're not getting the information, then it can hang because you are waiting for something to be true in your code, if. Instead, in practical systems, every 30 seconds or so, you just send it. Don't worry about if then else, right? But the result is still the same. So it's iterative. Okay, every 30 seconds you have to exchange this. Asynchronous means you do not need to synchronize these transmissions that, oh, at this particular time, everyone should exchange. It's not like that, right? You have your clock. If you want, you can just transmit every 30 seconds. Another neighbor, he started sometime else, somewhere else, and then he also does every 30 seconds. But they don't do at the same time. It's asynchronous, right? You just use your own clock and transmit. Doesn't matter who transmits when. As long as you are getting this information from your neighbors, you recompute and make sure that you keep your routing tables, forwarding tables updated, right? So that's the main thing. So it's iterative, but it's asynchronous. Asynchronous is very good because you don't have to rely on synchronous timing, which is very difficult to maintain in network, and if it's not synchronous, if there's any problem with the timing, then the algorithm can break. Another one is distributed. I have already highlighted that. So in link state routing, it's not distributed, it's centralized. It means that you have to get the entire global information of the network at your hand before you can compute the Dijkstra's algorithm. Here it's not centralized, it's distributed, so you just work on whatever information you have, right? And it's self-stopping, right? Self-stopping means that it will converge on its own. So if you let it iterate many times, it will converge. If there is any change in the network, the cost of a link has changed, it will propagate and it will converge. So again, the network will have the shortest path, right? All the forwarding tables will be updated in a way, so a packet from destination A to B will follow the shortest path, right? But self-stopping is kind of misnomer in practical systems because the practical systems continuously update this. So every 30 seconds you have to exchange, right? So there is nothing called stopping. Nobody knows actually whether it has converged or not. There is no global state. So no router can say that, oh, it has converged, so for me there is no need to exchange information anymore with my neighbors. You do not try to do that, because if something is wrong somewhere, then again there will be a deadlock. So although this is technically self-stopping, in real systems you never stop. Okay, is that clear? Any questions? So now we look at a small network with some real entries in the routing table to see the process of distance vector routing, right? So we have these nodes A, B, C, D, F, G, H, I, and if you look inside the routing table, then A only knows its neighbors. So A knows that to go to B, the cost is 8. It's we are using this way 8, that way also 8. Okay, so we are using symmetric links, so the cost both ways are the same, but they do not have to be like that, right? This is for simplicity. You can see A can reach to B, right? A can reach to D, right? So it can reach to B, it can reach to D, and that's it. It has only 2 neighbors, so it can reach 2. Rest of them are infinite. What is infinite? So who can tell me what does infinite mean? This is just an abstract theoretical representation on the slides, but in real life, what is it? Who can tell me? Yes, from the back? Can you raise your voice? Otherwise, I have to come back with the... It's not known. Yeah, exactly. That's what it means. Infinite means it's not known. So if something is not known, right, then how can you have it in your forwarding table, right? You don't have it in your forwarding table. So that's what I was trying to tell. In real life, if you do the tracing of the forwarding table, how it evolved over time, then at T0, the only entries that you will see are these 2, B and D. You won't see these infinites because it's actually not known, right? So it's not true that you are going to have entries and then you are going to put infinite. First of all, you don't know how many nodes are there. Who are they? Because you do not have any global information. There is no flooding in the network, right? So, in the beginning, you just have these 2. So, it only estimates the nearest neighbors only. And then, you have to exchange the information, right? So later you will exchange the information, and when you exchange, it means you're receiving, right? So if you're sending to your neighbor, it means your neighbor is receiving from its neighbor. You are also receiving from your neighbors. And when you receive, then you have to compute, right? So you have to compute. And when you compute, then things might also change. And then you again exchange, right? Remember, you periodically exchange. So when you exchange, you receive, and then you compute, then it changes, then you exchange again. So this process just goes on, like every 30 seconds or so, you have to keep doing it, right? And as a result, things should converge, right? Hopefully. Right. So that's the same thing. You keep doing the same thing, right? So if you keep doing it, then are you really converging? For example, will you be able to start with a small, minimal forwarding table in your router with your neighbors only, and then will it grow, and finally everyone will have the full routing table with the right costs? Okay, so we can actually look at this particular example, and this time we can trace the forwarding tables over multiple exchanges to see if they converge, right? So in the beginning, you can see A will have only this entry and this entry, 2 entries, and B will have 2 entries, 3 entries, right? It can go to E, so it can go to A with 8, it can go to C with 1, go to E with 1. And E, right, one entry, it can go to B with 1, it can go to D with 1, and it can go to F with 1, and it can go to H with 1, right? So E has 4 neighbors, as you can see. That's why it has 4 entries, right? B has 2 neighbors, 3 neighbors, so it has 3 entries. A has 2 neighbors, so only 2 entries, right? So far, so good. So every router, when you turn it on, right, give it power, it will do the hello exchange messages with its neighbors because it's connected already, right? And then it can find this information. So this is the initial table, routing table in every router, for example, right? Now the process starts. Now you have to exchange with your neighbors. So here we are saying at this time, B has received distance vectors from A, C, and E, okay? So we are combining. It's if you strictly follow up immediate update, like when you receive something from your neighbor, you immediately update, then it's only one update at a time. When you get something from a particular neighbor, you do the computation only for that information from that neighbor. But it would take a long time for us to trace. So in this case, what we are doing in this slide is we are just combining. You just delay the computation, if you like, delay it a little bit. So you aggregate the information from 3 neighbors, and then you compute at the same time. Just to show you, but if you are implementing, then you should immediately update as soon as you receive from A or E or C. So we are combined. A plus C plus E. So the information has come from A, the information has come from C, information has come from E. So this table, and this table, they have been all received by B before B does this computation, right? So B has this, sorry, C has this table. So B had this original table here, and this table has to change, right, as a result of receiving new distance vector tables from its 3 neighbors. And we are going to see how this will update. So this is the update of B. Okay, B has been updated, and we are going to see how it does the update. Okay, so we start with B's original. So it says that I can go to A with cost of 8, right? And A didn't, and A is also telling B that I can go to B with cost of 8, right? So remember that only this information, A and this information, because A can only give its estimate to B and D, because everything else is infinite, right? So these are actually not there. They're actually, so only 2. So look at the first one. A is saying I can go to B with 8, and B is the node. So this is useless information, right? Because this is not relevant. So the only relevant is this. A is saying I can go to D with a cost of 1. If you look at B's table, B doesn't have any entry for D. B doesn't know D. So this is a good information because B knows that if I accept this, right, then to go to A, the cost is 8, and A is saying I can go to D by 1. So one option is to have this entry D here. And if I go via A, the cost would be 9 because it's 8 plus 1 because I have to go to A, cost of 8, and A is telling me that I can go to D with cost of 1. Okay, so is that clear how I get 9? Is that clear? Any questions? Okay, so that's one neighbor. But we said that B has also received, right, quickly within a very small time frame from C, right? So have a look at C. Does C have anything with D? No, it doesn't have anything with D. So there is no information coming about D. But from E, it has some information about D, right? Okay, so E is also telling B that I can go to D with a cost of 1, and B has a cost of 1 to go to E, so it's 1 plus 1 is equal to 2. 1 plus 1, right, is equal to 2. So now B sees that it has two options, right? It has learned that it can go to D, which before it was not there in its routing table. So this is a good thing. It has learned a new destination, right? And it has two options. If the next hop is A, then the cost is 9. But if it goes via E, the cost is 2. So of course it accepts the cost of 2. So you see, 2 has been accepted. So here, couple of observations, right? As a result of exchange of the distance vector routing tables between the neighbors have learned. So in this particular case, B has learned a new route to D. And it has chosen the minimum cost, of course, right? So it learned that it could go via A and E, but it has decided to choose E. So the cost is 2, right? So this is something new. If you look at A, it doesn't have anything else to offer because the other one is 8 we have already considered, so there is nothing else. How about from C? So C, it learns about cost of B, but B is itself, so it ignores this one, right? And there is nothing else to offer, so C doesn't actually offer anything else, right? How about E? E is saying I can go to B with a cost of 1, but this is not useful because B is itself B here, but D is equal to 1 is something that we have used, but look at that. E is saying that I can go to F with cost of 1. So this is a useful information for B, right? Because before, B didn't have any entry for F. You see, these are all infinite. So it didn't have any entry for F. So now it will go to have an infinite for F, and it has to be via E. 1 plus 1 is equal to 2. So 1 plus 1 is equal to 2 because A and C are not giving you anything. So if you look at F, right, the only thing is 2, right? So this 2 is here. Okay? So it has learned F, and then same thing about H. So you can see H is also 2. And you can see H is 2. Okay? So this exchange was very useful for B. B has increased its routing table. It was very small, and now it can go to so many different destinations. In particular, it can go to, so before it could go to only A and C and E, only 3 entries. Now it has 1, 2, 3, 4, 5, 6 entries. Okay, so this is just exchanging with 3 neighbors. Is that clear how we got that? Okay, so in this slide, that's all we are showing, the update for B's routing table. Okay. So if you don't have any questions, it means you can follow this logic. So what we are going to do, we are going to see how this information propagates, right? So in the next one, we are saying that C receives distance vectors from B. Now C is receiving from B, but not the updated one. This is the updated B, right? But this updated B will be given to C at a different time. Let's say time T2, because T1, B received from C the original routing table, and let's say that C also received the B's original table during this time. Remember that every 30 seconds or something they will compute and upgrade and then retransmit. So we want to see how C would update if it received the original routing table from B, because the time is still T. So we are looking at the updates still at time T, but this time for C. So now we want to see how this will be updated when it receives this. So this is coming here to update this, right? So if you look at that, so B is saying I can go to A, but C doesn't have any entry for A, right? So this is the updated C. So definitely we are looking for a new destination A. So new destination A is now 9. Why is it 9? So it is 8 plus 1. So A is saying, B is saying I can go to A with a cost of 8, and C knows that it costs 1 to go to B. So it's 8 plus 1, 9, right? Good. So this is a new entry which C didn't have before in its routing table. So this is something good, right? The next one, C1 is not very useful because this information is going to C, but this is useful, right? So B is saying I can go to E with the cost of 1. And if you look at here, there was no entry for E, so now there should be an entry for E, and it is 2 because it's 1 plus 1, right? What else B had? Nothing else. So these are the only 2 updates we are expecting. So C is updated to this one, and it has 2 new entries. Before it has only 1, right? Only 1 entry, and now it has 1, 2, 3. Right? So now we are able to trace the progression or the evolution of the routing tables in each of the routers over time based on a particular reception from a particular neighbor, right? So that's what we are doing. And at T1, if you want to compute the routing table for E, right, then you can combine, in this case, that you receive from B, D, F, H, B, D, F, H, because these are the neighbors. And once, because we are talking about time T1, this iteration if you receive the original routing tables from your neighbors, what will happen, right? Same thing. And then you will see if you compute, then yeah, so you can update E, which is not shown here. So one thing you see is this. At T0, right, for example, if you look at C, right, at T0 in the beginning, only C knows its routing table. Nobody knows its routing table, right? But at T is equal to 1, in the next iteration, let's say every 30 seconds, some updates are happening, B will receive C's information, and B's routing table will be influenced by C's information. But for A, E, you need another iteration when B will transmit its routing tables. In that case, A and E are the neighbors of B, so in the next iteration, they will be influenced by the C's information. So C's information to propagate to A and E, which is 2 hops away, will take 2 iterations. Similarly, when they update at T3, H, D will be affected. So you can see H and D are 3 hops away from C, so that's why it takes the 3rd iteration to reach there. And at the 4th iteration, all of the nodes in the network will be influenced by C's original routing table. So you can see it's not flooding, right? Flooding is instant. If you want to send an information to all the other nodes, it's instant, right? It's just microseconds, maximum milliseconds of delay, and then it reaches everyone. But here it's not broadcasting, it's not flooding, it's just exchanging iteratively, let's say every 30 seconds or so. So it takes multiple iterations. So T4 means you can multiply 4 by 30 seconds, and then you can say, oh, all right, so it takes 2 minutes in this small network for a routing table's information to be propagated to all the nodes in the network. So this is a fundamental difference between link state routing and distance vector routing, right? It takes time to disseminate the information throughout the network to guarantee that the entire network will learn any changes anywhere in the network. It will take time. It's not like link state routing where you just broadcast or flood the information and immediately everyone will know. Okay, is that clear? Question?
When T equals 2, does it C is influenced by other routing also, or?
So your question is at T equals 2, does B update?
Like other way around. When you say C is influenced other, but other way around, does C is influenced by others?
Oh, is C influenced by others? Okay, I think I understand your question now. Let's see. So you're saying at T1, B receives C's information. So C is influencing B. At T2, because B is now broadcasting, C's information is influencing A and E. And your question is, how about C itself? It also should be receiving, right? Okay, so at T1, C gets influenced by B only, right? And then at T1, B is getting influenced by A as well, right? So at T2, when B sends again to C, C is getting influenced by A. So it's both ways. But in summary, right, if a node is 2 hop away from you, not the immediate neighbor, then you need 2 rounds of exchanges. If a neighbor is 3 hops away from you, then you need 3 rounds of exchanges before you can influence that neighbor, right? If you are X hop away, then it takes X iterations, right? It's just common sense, you can see, because it propagates through your neighbors only, and the neighbors exchange every round. So maybe it's 30 seconds. So in practical implementations, we'll talk about that a little bit towards the end, about the practical protocols. This is not the practical protocol. This is the theory behind the protocols, right? Bellman-Ford algorithm or distance vector algorithm. And all these explanations, as you can see, is the theory, how the theory works. In practical, you need some practical timers and things like that for it to implement in a real system. But we are not going there because it might distract you from the theory. So any other questions? So this slide basically is telling you why it takes n iterations to reach the n hop neighbor. In flooding, it's immediate. Irrespective of how far your neighbor is, it's immediate. Any questions at this point of time about distance vector routing? This particular slide or the previous slides? If you don't have any questions, I will highlight a problem of distance vector routing, which is a famous problem. And then in the next half of this lecture, we'll try to solve that problem, right? How that problem can be solved. So the problem comes from the slow convergence. As you can see, instead of reaching everyone immediately, it takes n iterations to reach the n hop away node, right? So there is this delay to disseminate any change in the network. And as we have discussed many times in the past, computer networks need to be fully autonomous. It means that no human intervention, it doesn't work anymore. So 50 years ago, it was manually maintained. The routing tables were created by the administrator, right? That this should be the next hop if you want to go to that destination and things like that. Anything changes, it requires the intervention of the human operator again to make things work. With today's scale, the commercial internet is no longer feasible for any human to intervene and change the routing tables, okay? Because the size of the routing tables are enormous, right? And the speed at which things can happen in the network and changes can happen is beyond the human reaction time, right? And if you do not fix it, then it will remain unstable. There can be loop in the network. Packets may be going around, packet may be dropped. Inefficiency will drop, right? It will take a long time to download a page because of the routing problem, right? So if you want to make it autonomous, it means that you would like any changes in the network to be reflected in the routing tables. Routing tables need to detect that there is a change in the network somewhere, and as a result, I need to change the entries in my routing table, the next hop for certain destinations, right? But because of this slow convergence, it's not flooding based, but repetitive exchanges in the next repetition cycles, there is a delay. And in the next half of the lecture, we are going to reflect on this, the influence of this delay in the distance vector performance. And we will highlight a particular problem that can create instability in the network, and then we'll look at a solution. So let's take a break, very short, 5 minutes, and then when we come back, we are going to talk about this convergence problem. Okay, we are about to resume the second half of the lecture today. So please take your seats and let's focus. So just before the break, we talked about the convergence issue, and the problem that you will find is the slow convergence, especially when a link cost increases. A link gets overloaded, which is the bad news. So we are going to see soon, and so next few slides you will see that although the network is very small, there are so many routing tables that you have to follow, as you can see, to understand the problem and the solution Poisson reverse, right? So instead, I'm going to follow a simpler, intuitive way to explain this, and then you can follow this on your own later, right? Because it's already in the slide. So let's try to understand the convergence thing, right? So this is a network that we are going to consider to explain and illustrate this convergence in distance vector routing. So we have three nodes, A, B, and C, and the numbers next to the links show the cost of the link at the time. So this link, and it's bidirectional, so from A to B the cost is 4, and from B back to A is also 4. Similarly, from B to C is 1, and going back from C to B is also 1, right? And this one is 50. So let's look at the routing tables, right? So these routing tables are shown slightly differently than we usually have done in the past. So let me just explain the format that is used in this particular slide. So this is for node A. So node A should have entries for B and C, because both of them are its neighbors. So this is the stable state, right, in the beginning when the cost was 4. So node A is saying that I can go to B, and B is the direct cost is 4. So this is how it will go. I mean, this information is not useful, which is not highlighted here. So the other one is saying, yeah, I could also go via C, right? But then you have to 50 plus 1, so it would cost 51. And I can go to C, if I go directly it's 50, so I would rather go via B, right? So it would be 4 plus 1 is 5, right? So this is interesting. Sometimes the direct route is costlier than if you go via a neighbor. So who can give me an example, practical example? So this is more convincing rather than me just saying that this is possible. Who can come up with a real practical example? Okay, think about link overloading, heavily utilized link. Okay, so in computer networks, you have studied queuing delay, right, in the first lecture, and you have seen that these queuing delays can dominate the real performance of the link, because before you can get to the link, right, you have to wait in the queue, right, and if this link is heavily utilized at that time in the network because it's a very popular link, right, then your packet will be waiting in the queue just to access the link significantly. And this is something you can avoid by going through a detour, right? Other links, you know, another node, and then those links are not overloaded. So this happens very often in the existing road network, right? You know the shortest route, but then suddenly this route becomes congested, too much traffic, and then you take a detour, right? So this is the detour example here. So I'm just telling you all of these things so you do not get confused that how come, you know, I can go to C via B only 5, but if I directly go to C is 50. It's because the detours sometimes are quicker than the direct path because of congestion, right? Okay. So similarly, here you can see, so one of the interesting thing I want to show you is the cost of 6. So this is node B, right? So node B is saying I can go to A, and if I go directly is 4, but if I go via C it's 6. Does it make sense? So this is very important because later we'll use this information to highlight the problem of slow convergence and also find out the solution. So who can tell me where this 6 is coming from? So this is a very trick question, or if you like, a trick observation, and it's not intuitive, it's not readily observable. So I'm just wondering if any one of you here can explain me why is it 6? And if you understand it, then you can follow all of these slides and you can follow today's explanation from me about the problem, the slow convergence problem in distance vector routing and its solution, Poisson reverse. Okay, so who wants to explain? Why is it 6? Yeah, I can see a hand there.
So it sticks because it goes via C, so it goes from B to C, and then it looks up the table and goes A.
Yeah.
And it says that the route there is to go back from C to B and then to A.
Yeah, okay, you are in the right direction. Break it up, let's break it up. So B, when you say look it up, what exactly do you mean?
It looks to the other forwarding table.
Yeah, so in neighbors they exchange, right? So you don't have to look up the neighbor's routing table, it comes to you because they exchange it. Yeah, I think she's in the right direction. Let me explain what she's saying. Okay, so why is it 6? So node B, right, exchanges its routing table to C, right, at some particular iteration, and B is telling C that I can go to A the cost of 4, and this information is given to C, right? And then C thinks that it can go to A via B the cost of 5. So C will have in its routing table that it can go to A the cost of 5, right? Look at this. This is what I'm talking about, right? Now, in another iteration, right, when C sends this information to B, right, B thinks that it can go to A via C with a cost of 6. Right? So that's the information 6 here. Of course, B actually doesn't make use of this information because this is the white information, this is the highlighted one, right? This is empty, this is highlighted. This is the highlighted information that is actually stored in node B's estimation, which will be exchanged. But this can happen because of that, right? Anyway, so we'll revisit this when we want to explain you the problem. But first I want to show you that sometimes there is no problem. So in this particular case, we have a good news. What is good news? The cost has decreased. This link has improved, right? Instead of 4, it's now 4 times better. It's 1. The cost is 1. So it means that the congestion has, relieved. Now 4 has dropped to 1. Now in this case you will see that this information doesn't cause any problem, and this 4 quickly becomes 1, and then it settles down very quickly, right? So it propagates very quickly. All the other nodes will get this information. There is no major problem. However, if you go in the other direction, right? So in the network, if a link suddenly becomes heavily congested, which is a bad news, right? Then you will see that this will create some instability and loop in the network because of the slow convergence and because of the problem I was telling you before. So now you will see that this 6 becomes highlighted because the other one has become 60. So previously this 6 was not used because 4 was actually used, right? This 4 was smaller than 6, so this 6 information was not there. But now, because the 4 has become 60 because of this sudden increase to 60, this 6 becomes very attractive, and 6 is retained by B as its the minimum cost solution in its distance vector routing table. And this is going to create problem. As you see, this 6 is not increasing quickly. This 6 is increasing very slowly and is tricking B, for example, node B. If it wants to go to A, right, the cost has gone from 4 to 60, right? So B should just accept it that, the cost has increased. Instead, B thinks, oh, I could go via C, and the cost is only 6, right? And then C thinks that, oh, the cost is 6, so the next time the cost will be another exchange, and then 2 will be added, going to B, and then B thinks is going via C again, so the cost becomes 8. And they keep exchanging this unrealistic value to each other for a long time until it gets incremented, and it becomes larger than 60, right? When it becomes larger than 60, then B will think that I don't need to go via C. I can go directly to A, and the cost is 60. But at the moment, it wants to go to A via C because it thinks there is a shorter route, because C is advertising saying that I can reach to A with cost of 6. So B thinks that, oh, okay, if I go to C, then the cost would be 6, so 6 plus 1 is 7, and then C thinks that, oh, okay, it's 7, then B can go to A with 7, So it means that the cost is 8 because I can go to B with 1, 8. So it's advertised as 8. And then B thinks, oh, I can go to A via 8 plus 1, 9. So B advertises this to C, and then C thinks, oh, 9, so it means 9 plus 1, 10. I can go to A cost of 9. These are actually fake, incorrect, unrealistic, but this is not caught in the algorithm because they are exchanging, and it has very strict rules that we have seen in the previous slides. In the computations, whatever is the smaller, they accept it, and oblivious of the fact that they are deceiving themselves, because the fact that C is advertising that it can reach to A with a lower cost than 60 is because C learned it from B in the first place, right? And then B is now believing C. And this is creating the problem. So a couple of things here. So this is slowing down, and this is called count to infinity problem. The reason it says infinity is because it has to increase slowly, one by one, in every round. So this is not a broadcast flooding that this information can be sent immediately to everyone. You just have to wait for the next round of exchanges, and it's just counting by one, increasing until it becomes greater than 60. So it's very, very slow in making this information known that this link has changed, right? And as a result, there is a loop here, and this loop will continue for a long time until this information gets installed in the routing table. So not all the iterations are shown here. It's just to stop. The similar things also happen for node C. It has 5, and then now it becomes 7, and then they continue like this. So if you look at node C, then it thinks that it can go to A via B. It's the same thing. So B thinks it can go to A via C, and C thinks it can go to A via B. So that's where the problem is. Okay, so I tried to explain this to you intuitively without going through all the other entries in all the other routing tables here, which will just confuse yourself. But a couple of things. Do you understand what I'm talking about? If you have any questions on that, I'll try to answer it here. The second thing, even if you understand this intuitive explanation, you have to go back and trace it, right? So until you trace all the entries here yourself by hand, it's not still clear. And it's absolutely important that you be able to trace it. So the first question first, do you understand why the loop is there between B and C? Because the solution will be based on this understanding. Solution is Poisson reverse. Any hand? It's a bit dark here. But if you have any questions, I'm happy to explain now before I show you the solution. Yeah.
Can you explain the loop?
Loop? The loop? Yeah. Okay, so the question is, can I explain the loop again? So if you look at this, to explain the loop, again, I can go back to the previous one. It's the same thing. So you see in the beginning, B has this entry that it can go to A with 4, right? And B will share this information with C. So C will know that it can reach to A with a cost of 5 because it has to go to B, which costs 1, and B is telling that I can go to A with 4. So C will have this information that it can go to destination A with cost of 5. Is that clear? Do you understand up to this much? Okay, now we go to the next round of exchanges, right? Remember, every 30 seconds everyone has to exchange their information with the neighbors. Now, so the next round, So if you look at, so we just, okay, so B had A4 and now C has received from B, so C has A5. So in the next round, we are going to look at B. So let's say that C is now advertising its routing table to B, right? So B receives this information that C can go to A with 5, right? So we are seeing why this 6 is there. So it means that B will update this information that if it wants to go via C, right, then the cost will be 6 because C is saying I can go to A with cost of 5 and there is a cost of 1. So it will be 6 here. But because B already has a direct link cost of 4, B is not going to make use of this information 6, right? So this information is not used by B because B already has a better link. However, in the next one, if this cost is 60, then B will make use of that, right? So B makes use of that, so the cost is 6. Now B is saying that I can go to A with cost of 6 via C because from B to A the direct cost is very high, so it accepts it, right? And C had this information that I can go to A with cost of 5, right? And because it advertised it to B, B has updated its information from A to 4 to A to 6. Is that clear? Okay, next round, if you go to the next round, right, then let's say that B is now advertising this information to C, right? So C will see that, oh, my neighbor B is telling me that it can go to A with cost of 6, right? But if I go directly, the cost is 50. So I would accept it, and the cost would be 6 plus 1, 7. So for C, it will be A 7. Okay? Is that correct? Yes?
It doesn't remember that A equal 5, C to A equal 5.
Yeah, it's because of this cost. This cost has increased to 60, right? So remember before it was A4. So if instead of 4 it becomes 60, right? Then when C advertises A5, B will accept it as A6 because the cost is 60. Cost is 60 and A6 is attractive. That's why it will keep it. So it all depends on what's the cost of the neighbor. If it is worse than this, then it will be tricked into believing it. Was that your question? You don't look very convinced. Okay. So count to infinity problem. So C now have A7, right? When it receives A6 from B, it will have A7. And this A7, when it goes to B, right? B will think that, oh, my direct cost is 60, but if I go via C, then it will be 7 plus 1, 8. So B will update its table to A8. Right? And in the next round, B will advertise this A8 to C, right? So C will make it A9, right? And then when C sends this A9 to B, B will make it A10, because this 10 is still less than 60. So every round, they increase by 1. And it's count to infinity. It's basically count to that very large, big value before it learns that there is a problem. So the packets, what happens in the packets, when the packet arrives at B, B forwards it to C. When the packet arrives at C, C forwards it to B. But the destination address is A. It's never going to go to A. It's just going back and forth, A and B. And A and B are updating their routing tables every 30 seconds. Within 30 seconds, this packet can go back and forth many times because the speed of the link. So this is the slow convergence problem. That can happen. This is a very specific example crafted to show you the problem. In real life, this problem can happen or not happen sometimes. But when it happens, then this is what's going to happen. Routing loops will be created. Any other questions? Yeah, so this is the main problem to understand, how the routing loop can be created in distance vector routing. So I have one example here. You should be able to create another example. Whenever a link cost increases significantly, this can happen. So that's the bad news. So the bad news can create this problem. It doesn't propagate very quickly like the good news, right? Because of this problem. Right. So at least if we understand the problem, then we should be able to explain why we arrived at this problem in the first place, why we have this problem. So who can tell me why we are having this problem? B knows that the link to A has gone up, the cost of the link, it has become 60. B knows that, right? How come B is fooled to think that there is a shorter route via C? So that's where the problem is. There is no route, shorter route via C. So why we are having this problem? Because
orbit choose a minimum
Yeah, always, you are always choosing the minimal cost, and B doesn't have the necessary intelligence within the protocol to understand that C is actually relying on B to give this information, that I can reach to A quicker because of your previous routing table that you sent to me saying that you could reach to A with 4, right? So whatever C is promising to B, that's actually based on what B promised to C in the first place, right? And now B is a victim of this because B doesn't have enough intelligence that C is giving this smaller cost to A based on C's understanding that it would be able to forward the packet through B, right? Because C is not telling that information, that by the way, I can reach to A with only 6, by the way, that packet will go through you. If you just told that, then B would reject it, right? But what are they exchanging? So here the important thing is, what is it that in distance vector routing they exchange? So one thing I have not told you so far is that they exchange only the destination and the estimated cost. In your own routing table, you have 3 columns. I mean, you have many columns in practical systems, but for the theory part, you have 3 columns, right? You have the destination, you have the next hop, and then you have the estimated cost, right? And when you are exchanging only the destination address and the estimated cost. You are not exchanging the next hop. So when C is saying that I can reach to A with a smaller cost, C is not telling B that, by the way, this is through you. And that's where the problem is. So B doesn't know that C is thinking of sending it through me. B doesn't know that, and that's why it's accepting it. Okay? So I'm going to annotate here, showing you these 3 columns and these 2 columns that are exchanged, and the problem is. So we have a deeper understanding of the problem, not just what the problem is, why the problem is caused. Because if we don't know why the problem is caused, we cannot find the solution. Just because you know there is a problem doesn't mean you can have a solution. You have to understand and analyze to see what is causing the problem. That's why I'm going to annotate, which is not in the slides. But that's okay, I'm here, so I'll do this, what I've just said. 3 columns. Destination, next hop, and the estimated cost, 3 columns, right? So the routers maintain 3 columns, right? So when you exchange 2 columns, destination and the cost. Okay, so they exchange only 2 columns. They do not exchange the next hop. That's what's the source of the problem. And that's why B doesn't have the necessary intelligence to detect that this attractive cost advertised by C is not valid. Okay? So if C was to advertise 3 columns instead of 2 columns, then C would say that I can reach to A with a cost of 6, only 6, and the next hop would be you. And then B would say, oh, me. No, that's not possible because the link has gone up, it's now 60. So let's discard it, right? It would have been much easier. Unfortunately, because of this protocol, what gets exchanged prohibits B from reaching that decision. And as a result, we have this problem, routing, loop problem. Is that clear? So this critical information was not explicit in your slides. So I've just added that with the added explanation. So go back and listen to this lecture again. And now we are going to look at a solution, an improvement in the protocol so that this can be addressed and these loops can be avoided. So the solution that we are going to see next, for the solution I need at least 5 minutes. Yeah, we have 15 minutes. I want to take a slight detour, right? The solution is Poisson reverse, which is the protocol enhancement from RFC, which is implemented in all the products, commercial products such as Cisco routers. But the one that I'm going to tell you is slight detour. Okay, so the problem we said that is because you are not exchanging 3 columns. So what if? So one solution could be always you exchange 3 columns. That would fix the problem, right? So this is solution 1. You exchange 3 columns, but we cannot do that. That's already implemented. They exchange 2 columns, right? They don't exchange extended routing table. They exchange only minimal information. So what is the solution? If we stick to that, if we say, oh, standard says that you exchange only 2 columns, the destination and the cost. What solution is needed so that we do not have the routing table? That's called Poisson reverse. What is Poisson reverse, right? So the name is strange, and you have so many slides. So basically, what is trying to tell is this rule, but I'll try to give you a more intuitive explanation to this rule. Remember, we said that the reason that B believes that there is a shorter route via C is because B doesn't know that C got this smaller route via B, right? B actually gave that information in the beginning. So one way to stop this problem on its track is that C actually knows there's this smaller cost that is this attractive cost of 6 that is advertising to B is via B. So C knows that information anyway, right? So what C can do is not advertise it. It means do not advertise a cost to a destination to your neighbor if your neighbor is the next hop. Because you do not want to tell your neighbor about a destination that you are going to send through your neighbor. Your neighbor is in a better position to know what is the recent cost to that destination. You should not tell your neighbor because your neighbor is the next hop. So if your neighbor is the next hop, then do not advertise that particular routing entry to your neighbor. So the solution of Poisson reverse is instead of advertising 3 columns, right? Advertise selected rows of the table. Eliminate the rows that are the next hop. Your neighbor is the next hop. If your neighbor is the next hop in any of the rows, do not advertise that row of the table. Okay? So instead of increasing the number of columns in the table, you reduce the number of rows in the table and still keep it 2 columns. Is that clear? So if C doesn't tell B that I have an attractive cost, then this problem wouldn't happen, right? Okay, so to make it more concrete now, what we are saying is that if you do Poisson reverse, yeah, you have to trace a lot of things here. Maybe I go back to my annotations, because you got used to this annotation now. You understood it. So you see all these next rounds, C should not, we should cancel. This is Poisson reverse, right? C should not tell B that I can reach to A with cost of 7, because C knows that the next hop is B, so it should not advertise that to B. It should advertise some other things where the next hop is not B. So that's Poisson reverse. You cross that out. You do not advertise certain rows of your table.
And how would we like decrease the columns? How would the machine like collect more?
Not column, rows.
Oh, right. So how like the
Yeah.
round
Yeah, good question. So how the protocol will decrease the rows? I have not shown you the rows, right? So let's say this is for router B, right? No, so let's say this is for router C. And router C is saying that if I want to go to destination A, then my next hop is B, and my cost is 5, right? So I'm taking this information here. Okay, is that clear? And it says that I can go to B, my next hop is B, and the cost is 1. Okay, that's fine, right? Now, C wants to advertise, right? So you want to advertise. So we are saying advertise to B. You want to advertise your routing table to B. So first of all, you don't advertise this column. You advertise these two columns, right? Destination and cost. But not all the rows, right? So this row, should it be advertised to B or not? That's the question. Yes or no? Should C advertise this row to B? No, because you can see in the next hop column it says B. Because of that, this row will not be advertised to B. So your question was how the protocol knows. It looks at this column, middle column. If the next hop is B, it will not advertise this row to B. So the protocol has this information now to act. Does that answer your question? Okay, any other questions? Okay, so if you do Poisson reverse, it means that if you have learned, if C has learned this cost from B, right? Of course, it has learned this cost from B. That's why the B is the next hop, right? Then it should not forward that to B. That's Poisson reverse. That's all. That's what all it is, and then you can trace. Go back and trace it. One other thing I want you to, I'm not going to go through it here, but I leave it as an exercise to think, reflect, and see if Poisson reverse would catch all the problems. Like even if we implement Poisson reverse, can we get into a situation where we can still have count to infinity problem? So I leave that as a homework to you, and we are happy to discuss that in Ed Forum if you have problem. What we are switching now is to comparison between link state and distance vector routing, because we said that once we do both of them, then we will be in a better position to discuss the differences. So you can look at the complexity. We have already seen that it has exponential complexity due to Dijkstra's shortest path algorithm. You can reduce it a little bit to logarithmic, but still it's complex. Instead, DV exchange between the neighbors, and it doesn't have this n, because if you have only two neighbors, then you only worry about two neighbors, right? You don't care about how big the network when you are exchanging your messages, because you don't have to exchange with everyone, right? Is that clear? So the first one is how many exchanges you are making. So you only exchange with your neighbors. So if you have two neighbors, you don't care if you have 100 or 50 nodes in the network. But in link state, your computations are based on, and the messages are transmitted to n squared, the message complexity. The speed, by now, you already have noticed perhaps that its convergence is slow, right? And it leads to count to infinity problem. And in link state routing, yeah, so these are the two main differences, and the rest of them not very important. But remember the real protocols. So we talked about the abstract theories like link state and distance vector, but if you look at the actual software, then you see it's OSPF for link state and it's RIP for distance vector. Okay, so let's do a couple of quiz to finish it off. We have a couple of minutes. So the question is in the link state routing, so link state routing, each node sends information of its direct links to who does it send? Immediate neighbors? A? Anyone thinks? Any hand? Second, all nodes in the network? Who thinks it sends it to all nodes? Yep, I can see 2, 3 hands. Who thinks only one neighbor? Yeah, no answer, fine. And none of them. So the answer is B, right? You do a flooding. You flood throughout the network, so you want to send the information to everyone, right? But in distance vector, who do you send it to? You share the distance table with who? A, all immediate neighbors, all nodes in the network, any one neighbor? Which one is the correct answer? A. A is all immediate neighbors, correct. So you exchange it only with your immediate neighbors. That's all, right? So the correct answer is all immediate neighbors, or all neighbors if you like. Okay, which of the following is true? Right? Always read, we are asking for not true or true, right? Of distance vector routing. Convergence delay depends on the topology. Convergence delay depends on the number of nodes and links. Each node knows the entire topology. Is this correct? Each node knows the entire topology.